Okay, that last video was a little bit longer than I had hoped. Hopefully this video will be a little bit shorter. We're going to conclude this chapter with a discussion of torque. Consider I have a rigid body. By rigid we mean if I apply a force on it, it will not change the shape of the body, will not press it in or anything. It's going to stay rigid. So the force will only move it. It will either move it translationally or rotationally. Well, let's say we have it fixed about some axis, so we only expect it to move rotationally. And if I apply a force like this, the only part of that force that's going to cause it to rotate is going to be the perpendicular component. That's going to cause it to rotate around like this. The radial component of that force is just going to pull on it on the pivot point, and that's not going to make it do anything because it's already secured. So only that perpendicular component is going to cause movement, and hence that's all we need to really consider as far as what we call torque. We're going to define the torque as being equal to the distance to that point where the force is applied times the perpendicular component of this force. Now if the angle between that radial direction and that force is phi, then the perpendicular component is going to be equal to F sine phi. And hence we'll have this distance r times this perpendicular component F sine phi, and our torque will then be r times F sine phi, where phi is the angle between the direction, the radial direction, and the direction of the force. So torque is r times F sine phi. We'll have units of newtons meters. If we were to extend the line of action of our force, so if I have a force like here, and I extend a line of action, which is a line that is infinitely long, along the same direction as the force, and I found the shortest distance to that line of action, I'm going to call that distance the moment arm, and that will be this distance d. So the shortest distance from the axis to the line of action of this force is going to be the perpendicular distance to that line, and that's why I call the moment arm d. The torque can be defined as the full force F times that shortest distance d. That is torque. Full force times the moment arm, the shortest distance to the line of action. If you can think of torques in this way, as a force times its moment arm, it will take you half the way through a course in statics. Believe me. Now, it seems pretty easy enough, but you have to think of it this way. Force, shortest distance, moment arm, that is torque. Note that if I look at this triangle here, the hypotenuse of that right triangle is r, and so this distance d, this being phi here, this distance d is equal to r times the sine of phi. So my moment arm is equal to r sine phi, and if I were to substitute that in to torque equal to F times d, I would get torque equal to F times r sine phi, which is the what we had on the previous screen. So this is actually consistent with the result that we had on the previous screen. So force times moment arm is torque. Let's say you got stuck on the side of the highway and you have a flat tire and you have to deal with that situation. What are you going to do? Well, you could call somebody up and have them come out and help you, or maybe you could try to change the tire yourself. Now, so you go in the back and you find a wrench. Maybe not, you probably won't use this kind of wrench, but you find some kind of crowbar or wrench and you put it on the lug nut and you try to turn the lug nut. Probably would have the wrench the other way around, but you try to turn the lug nut and it won't budge because the last time you had your tires changed, you had taken it into the shop and they used one of those pneumatic impact wrenches and they tightened it beyond human capability of loosening. So you have this wrench and you're using all your force, and you really need to be about 3 times stronger in order to turn this lug nut. So what do? Well, you go in the back of your car and you pull out a bar that you can put over your wrench to increase your moment arm. And maybe you can increase your moment arm by 3 times, and hence you can apply the same force that you were applying before, but now you have a moment arm that's 3 times longer. So the torque you're applying is 3 times greater. So you can use this mechanical advantage, apply the same force as before, but now you have a 3 times greater torque because your moment arm is longer, and hence now you can turn the lug nut. So this is a nice little thing to be able to do. Increase your moment arm gives you a greater mechanical advantage for torque. Apply the force, and voila, a new wheel. Let's try another example. You've gone fishing. Your fishing pole is 2 meters long and it's inclined to the horizontal at an angle of 20 degrees. What is the torque exerted by the fish about an axis perpendicular to the page and passing through the fisher's hand? We'll talk about that direction in a moment. The tension of the line is 100 newtons. So you're a fisherman, and the fish is going to pull on your line at 100 newtons. What we're really interested in is our moment arm and our perpendicular force. So we want to find the component of this 100 Newton force that is actually perpendicular to our fishing pole. The angle of this pole here is 57 degrees. So if I were to find this right triangle here, the perpendicular component of this force is going to be equal to 100 newtons times the sine of 57 degrees. So that will be 100 times the sine of 57 degrees. 84 newtons will be our perpendicular component. So if we actually had a fish on the line, some fish, pulling on that line, we'd have a moment arm and a perpendicular force of 84 newtons. So our torque is the force times the moment arm. 84 newtons times 2 meters for the length of the fishing rod is 168 newton meters. Now the direction that torque is a vector, and the way to determine your direction is to use a right hand rule. If you curl your fingers in the direction of the rotation caused by the torque, the direction of the vector torque is the direction given by your thumb. So in this case, if this fish were pulling out like this would be rotating clockwise as you're looking at it. And if I curl my fingers clockwise, my thumb will be pointing into the page towards me, which would be the negative z direction. So I would have a negative z direction for my torque. As I indicate that on this, that would be into the page. What I mean by into the page, you're looking at the tail feathers of the arrow as it's going into the page, and that's what the X means. You're looking at the tail feathers of that arrow as the arrow is going into the page. If the arrow were coming out of the page towards you, you would just look at a dot in the middle of that circle as you're looking at the tip of the arrow coming towards you. So we actually have a sign convention for torques. We use positive torques for counterclockwise rotations. That means you're going in the positive z direction outward here. And we use negative for clockwise rotations as you're going in the negative z direction into the page. So counterclockwise is positive, clockwise is negative, according to the right hand rule for the rotations. It's the same way a screw would move in or out of the page if you were to tighten or loosen the screw. If you were to tighten the screw, you would go clockwise, and that would force the screw inward this way in the negative z direction. If you were to loosen the screw, it would go counterclockwise, and that would loosen it and pull it outward in a positive z direction. Let's try this out in this problem. We have a wheel with an axle. We have 3 forces acting on this wheel, trying to cause it to turn. So we have three torques. A couple of these torques are in one direction and the other torque is in the opposite direction. So we'll find the net torque on this wheel. Now distance radius A is 10 centimeters and radius B is 25 centimeters. We have two forces that have a moment arm of radius B, and one force has a moment arm of radius A. 30-degree angle here is not going to matter because that 12 newtons does indeed have a perpendicular moment arm of radius A. So our net torque is going to be, we're going to have two negative torques because the 10 newtons and the 9 newtons are trying to make this thing rotate clockwise, which would be a negative torque, and the 12 newtons is trying to make this thing rotate counterclockwise, which would be a positive torque. So we have a negative 10 times B plus a negative 9 times B plus 12 times A. And those are our three torques. So we have a negative 19 times distance B, which is 25 centimeters or 0.25 meters. We have a positive torque of 12 newtons times distance A, which is 0.1 meters, giving us a net torque of a negative 3.55 newton meters. So all things considered with these forces, a couple of forces are trying to make this rotate one way, the other force is trying to make this rotate the other way, and finally we end up with a net torque of a negative 3.55 newton meters. What that means is ultimately this thing is rotating clockwise as this net torque is trying to make this, or giving us a torque vector in a negative z direction, and we would indicate that by another X going into the page as you're looking at the tail feathers of that arrow. So, consider this. Let's say I had a point mass going around in a circle, and we have a tangential force acting on that point mass. We know from Newton's second law that that force would be equal mass times tangential acceleration, ma. F equals ma. Sounds good. But we might also consider that there might be a torque associated with this movement of this mass under this force at some radius r. So we would say that that torque is equal to this tangential force, which is perpendicular to that radius, times the radius to that point. So the torque about some origin for this particular mass would be equal to mass times tangential acceleration times r. So far, so good. We could write this as mass times angular acceleration times r, because that's tangential acceleration by our linear conversion. So a is equal to alpha times r times r. Let's factor this, and we would have that this torque is equal to mr squared times angular acceleration alpha. Well, you might notice for a point mass going around the circle that its moment of inertia at some radius r is indeed mr squared for a point mass. So this mr squared is indeed the moment of inertia for this point mass, and so our torque is equal to the moment of inertia I times our angular acceleration alpha. That is indeed the net torque for an object. It is equal to the moment of inertia times its angular acceleration. And know how closely this result resembles the net torque for a mass moving with linear acceleration. F net is equal to ma according to Newton's second law, but Newton's second law for torques for rotational motion is the moment of inertia times angular acceleration. So if we make the substitution of moment of inertia for mass and angular acceleration for linear acceleration, we make the correlation of net torque for net force. So this is Newton's second law for torques. And it kind of makes sense because moment of inertia is the rotational analog for mass, measuring the resistance to changes in motion, and angular acceleration is the rotational analog to linear acceleration. So torque is a rotational analog to force. In this particular case, where we're going counterclockwise, that torque would actually be out of the page towards you. Consider a problem. Here's an example problem. A uniform rod of length L and mass M is free to rotate by a frictionless pivot at one end in a vertical plane. The rod is released from rest in this horizontal position and allowed to fall. What is the initial angular acceleration of the rod and the initial linear acceleration of the right end of this rod? Well, we'll treat this as a torque problem, and we really have two ways to express the torque now. We can say that our net torque should be equal to the moment of inertia of the rod times its angular acceleration. And that would be one expression for the torque. But also we could say that our net torque would be equal to the external force times its moment arm. In this case, our only external force is gravity, mg. And the moment arm for that, well, we're going to treat gravity as acting at the center of mass of this rod, which would be right in the center. So it's going to be this force, mg, times the moment arm of L divided by 2, because at the center of this rod, it is a distance L divided by 2 away from the pivot. So, moment of inertia of a thin rod about its end is 1/3 ml squared. And multiply that by alpha, that's 1 torque. And the force we're dealing with is mg, and its moment, its moment is L divided by 2. So equating these two forms, we have 1/3 ml squared alpha is equal to mg L divided by 2. M's cancel out, one of the L's cancel out, and solving this for alpha, we get 3g divided by 2L as the angular acceleration of this full rod. The whole rod at once has the same angular acceleration all the way through the rigid body. So what is the linear acceleration for a point on the end here? Well, that is a distance away from the pivot of L, and the linear acceleration is always equal to the angular acceleration times the distance to that point, which in this case would be L. So the linear acceleration at the end of the rod would be L times alpha. Alpha is 3g over 2L, and L is L. L's cancel out. The linear acceleration at the end of this rod is not g, it is 1.5 g. It's 50% greater than g. Wow. How about that? How can that be? The only force acting on this is gravity. It's acting at the center of mass mg, but at the end here, the end is actually moving at a greater acceleration than g itself. That would have to do with the fact that if this were indeed a rigid rod acted on by gravity, that this point is going to actually go through a greater arc length than, say, points more to the interior. The center here is going to go through a smaller arc. As we go closer to the pivot point, we're going to go through a smaller and smaller arc. So the actual distances traveled in the same amount of time will be different. As we get further and further away from the pivot point, we're actually going a greater distance per time at the very end, and our linear acceleration at that moment is going to be 50% greater than gravity. Imagine this. You have the Leaning Tower of Pisa, and if it starts to fall, the point at the very top is going to be going at a greater acceleration than gravity than points more to the interior. For that to happen, the internal stress of the object itself must be able to hold itself together and pull that point in order to maintain that acceleration. If it can't, then as this starts to fall, it will break and it will snap in two as it starts to go down. You may have seen this happen when you see demolition of some buildings that have old smokestacks, as the buildings start to go down, the smokestacks start to tumble. They never were meant to be under that kind of stress. They always were meant to be vertical with gravity going straight down. So as they start to tumble, they will snap on their way down because the smokestack does not have enough rigidity to handle that stress and maintain that acceleration on the end. Same thing would happen if you were to kick over a children's toy block tower. Don't do that because they'll be upset. But if you were to do that, as the block tower went down, it would snap and you would see it not maintain its its linear acceleration on the end as it fell. A similar example, I'm giving you all sorts of examples here. When the Titanic sunk, then the front bulkheads filled up with water. The ship was forced out of the water like this. It was never meant to be out of the water. So as it came out of the water on the back end, it snapped in two, and this back end righted itself so that it looked like it was floating on the water again before it was pulled back into the water from that point. Some of the survivors would say that as they were in the lifeboats far away from the ship, they saw the ship come out of the water, and then they saw the ship apparently right itself. So they thought, whoa, the ship is okay. Maybe we should paddle back, get back to the ship, and get back on. But what really happened was just an illusion that the ship had snapped in two, and it came back to the water. Looked like it was righting itself, but actually, half the ship was already underwater, and that pulled it down after that. We conclude this lecture with the work done by a torque during a rotation. If we were to integrate a torque over the angle, we'll get the total work done by that rotation. And power would be the infinitesimal change in work in an infinitesimal amount of time. That would be the torque times the change in angle per time. Change in angle per time, d theta dt, is actually the angular velocity. So power for rotation is equal to the torque times the angular velocity omega. Note how similar these are to their linear analogs. Work done for a linear motion is force times linear displacement ds integrated over r displacement. And power is force times linear velocity. So power for linear motion is force times velocity. Power for angular motion is torque times angular velocity. Very good. We have concluded our total analogy. The forms of these equations are the same. We just have different variables to deal with in dealing with these situations. That is our third lecture for Chapter 10. We are ready to go on to Chapter 11 and